Previously, I talked about two different ways to threshold. To come up with the control the force particle rate at the whole brain level. So one approach is purely based on the cluster size, but based on the spatial extent. So sometimes I call it like the mountain approach. You have different mountains, so you compare the mountain. So the one approach is like the cross section, the area. So that's why the primary threshold approach. So the mountains you cut at some level, then you compare how much the area at that is section cut off. So that's both quantum field theory, SPM, and Monte Carlo simulation approach in Affinity. Both approaches adopt that. So that's with that approach, you have the voxel-wise threshold, that's the primary threshold. Suppose you choose the p-value at the voxel level is 0.01. So you find all the clusters. Then you do something else to come up with the cluster threshold. Suppose it's 55 voxels. Then you come back to your real data. For those clusters with that primary threshold, if you are greater than 55, then okay, then you say, we can talk about those clusters. Otherwise, forget about it. So even though this cluster is 54, just one voxel less than that is so whatever threshold, then people can't do anything about it, right? Just one voxel different. Is that really that important? So that's immediately we face that problem, right? So just one voxel difference, we cannot talk about it because nowadays the journals reviewers they're very picky about this so-called p-value thing, this force particle rate. So that's one problem. Another problem is that they focus on the spatial part, then that it cut it off. It's just artificially to in reality the brain, even though it's let me put it this way: the null hypothesis itself, it's a straw man. In reality, nobody cares about that the so-called the zero activity, low activation. In reality, the real situation is we already know the whole brain, pretty much almost all regions are some extent activated. You don't get exactly zeros in the brain. All the voxels except, for white matter, CSF, maybe you can say the low activation. For all the gray matter, nobody can make a claim a region is really zero. So that the starting point of null hypothesis, a beta is zero, that's just not reasonable to start with. So the more reasonable approach is it's not the null hypothesis itself. It's something we can with more confidence to make such a claim instead of based on the p-value. That I'm going to skip actually that criticism about the p-value thing. There are many ways people have been debating about this for many years. So I'm going to skip another criticism about this. The p-value thing. So let's say what can we do better. I'm going to skip this as well. Let's use the real data to demonstrate the alternative approach. So this is the typical FMI data, but we focus on the RI level. So in this case, we have 124 subjects. All of them are kids. So the data is a within state data. So for each subject, they performed correlation analysis, right? Within state, there are many ways to analyze, but this is the traditional approach. You pick up a theta region, you want to calculate the correlation between this theta region and the rest of the brain. So you have this correlation map. Then you convert to z-score, Fisher z-score. So you have that Z map per subject. So with 124 subjects, when you go to group level, you have 124 z-score three-dimensional volume data. So group level, suppose the model is, we have this, it's regression model. It's a simple regression because we have one experimental variable, which is behavior data. It's I believe it's a theory of mind measurement. So the model is at each voxel, you have the y on the left-hand side, y is the z-score. That's a zeta-based correlation. On the right-hand side, you have the intercept, you have the x. X is there's a theory of mind measurement for each child. So that's if you do the traditional approach, you have this simple regression model, right? General linear model. Then you suppose we care about the effect is the B, the theory of mind effect at each voxel. So if we do that at the whole brain level, this is the scenario we have. So depends on which primary threshold. In this table, the first row, the voxel-wise threshold is 0.01. That's pretty much nowadays the journal or the journals or reviewers demand use 0.01, right? So in that case, if you actually use Monte Carlo simulations, we haven't talked about that yet, but you run simulations with noise, but also you have the spatial structure, then you decide the threshold. In this case, the number of voxels is 28. So whenever you have the cluster which is 28 or above, then you can make a confident claim, talking about the theory of mind, that behavior effect. So there are only two clusters that managed to survive that threshold. That's on the last column, those are the two RIs. So if you adopt a different threshold, 0.005, that's the second row, then the threshold, of course, you need to be more lenient, right? So the cluster has to be bigger. That's the concept, and it's very intuitive. That threshold is 6 voxels. So then you have 4 clusters. You keep going, move to 0.01. That's probably a little bit difficult to pass those reviewers. But if you do that, the cluster size threshold is 106. Then you still have 4 clusters, right? You keep doing 0.05. I mean, that's definitely nobody will. I mean, journals will not accept. But if you do it anyway, it would require 407 voxels. In that case, there are still 6 clusters managed to survive. So there are 2 things I want to mention here. First of all, it's a little bit arbitrary, right? So it depends on what kind of a primary threshold you may end up with slightly different result. Notice the first row, you can claim 2 clusters. The other 3 rows, you get 4 clusters. So it's a little bit arbitrary. That's troubling. I mean, which one do you trust, right? I mean, it sounds like, should be a little bit more vigorous. But this arbitrary is definitely putting us in a dicey situation. So that's one problem. Another problem is this spatial extent is a nice approach, is a reasonable approach. Let me put another hypothetical scenario. That scenario is suppose you have 2 clusters, right? One cluster, suppose just focus on the first row, we're pretty happy because that cluster is above the threshold 28. Suppose it's 30 voxels. Okay, nice. Everybody's happy. We can say something about that. The second cluster is only 20 voxels, but that's just the cluster size. How about if we ignore their signal strength? We're not talking about the beta value. We're just based on the t statistic. So is that a reasonable approach, just based on the t statistic, ignore the signal strength? Even though the second cluster may be even stronger, the signal itself is stronger, but simply because the cluster is smaller. The smaller can be many reasons. Can be, of course, the sample size, or can be just anatomically, intrinsically, that region is smaller, right? Why do we need to penalize those regions that are just anatomically smaller? Is that reasonable? Is that a nice approach, right? So there are many ways we can criticize the current approaches. So we can do better to avoid those kind of dilemmas. So how do we do better? That's why I call the current approach is inefficient. Why is it inefficient? There's some information we throw away, we ignore, we don't take advantage of what kind of information. So that's the point I want to keep focusing on here. So remember this slide here at the bottom, that's the Voxel-wise approach, right? So we'll have that equation at the same, suppose that if I do the RI level, suppose we have some number of RIs. Basically, that's the same model for each of the RIs. So that's right at the top. So those are the equations. Suppose we have some number of RIs. So 20 RIs, we would have 20 equations like that, right? So each equation is just the group analysis. So we have 20 models. So if that's pretty much like Voxel-wise approach to the whole brain. But now I'm switching to the RI-based methodology. So in the end, if we do that like we do the whole brain, 20 RIs, we have 20 equations, 20 models. We solve it, then immediately we face the problem, right? The multiple testing problem. So if we perform it, of course, that's just not a viable solution. It's the penalty is just too much for us to handle. So that's why in the field, pretty much nobody does RI-based analysis. Well, that's just main reason. Occasionally, you may say that in the paper, that's probably focused on only a few RIs that can afford such a penalty. Otherwise, you don't only say people do RI-based analysis for whole brain. For example, you have 200 RIs. You don't say that. That's because that penalty, right? So that's our starting point. Suppose we just have 20 RIs. In this case, actually, we have 20. I believe it's 21 RIs in this real example. So what can we do better? Well, let's look at the equation. I condensed them. It's the same 21 RIs. The reason the traditional approach is that look at the A and B, the intercept and the slope. They are, even though they are 21 RIs, those intercept, we don't make assumption. They just behave independently among those 21 RIs, right? So we have 21 models. Those 21 models are totally independent with each other. Just like the whole brain. Suppose we have 200 voxels, we solve 200,000 equations, but we assume those 200,000 equations totally independent of each other. They don't share any information, even though they do have some kind of a similarity. What kind of a similarity? That's my starting point. So we can take advantage. They do share some commonality. What is that commonality? Well, we're not talking about random things. They're not totally independent with each other because here we're talking about the brain response. In this case, it's some behavior data effect. They do even talk about the brain response. They are not totally random number. They don't go wild from minus infinity to positive infinity. They are not like that. When we talk about the brain response, the percent single change, it would be, it's at the most, it's 3%. That's at the most. So they're probably roughly in some narrow range. So we can use that information. That's called a partial pruning. Why it's called a partial pruning? So instead of 21 separate models, we're going to put them together with one model. So that's the pivotal point. But when we put it together, that means we have to somehow code the RIs as a variable in the model. So that's why we have that extra variable, that Greek letter here, this one. That codes the RI variable there. So once we do that, then actually that's the subject. That Greek letter is subject. I misspoke. So we put into one model. We need either that Greek letter to code the quasi-subject variability. That's the extra term, right? In addition to that, we also do something different from the traditional approach. A and B, A sub I and B sub I's. Previously, those are treated as constant, as we don't know them, but they are constant. They are parameters. But now, here, we don't assume they are constant. They are random variables. So that's why in the model, look at the second row, I make assumption that A sub j, B sub j, they follow some Gaussian distribution. So that's another thing. I mean that is the crucial point. So I don't assume they are constant. I assume they follow some Gaussian distribution. So that's the thing I do. It is dramatically different from the traditional approach. So we treat them as random variables. So that's why I loosely bound them with that Gaussian distribution. That distribution, of course, we just assume the distribution, but we don't know the mean, we don't know the variance. We're going to use the data to find out what's the mean, what's the variance for each of the two parameters, the intercept and the slope. So that's the crucial part. So the traditional approach, A sub j and B sub j, they are parameters, but they are fixed. We just need to estimate them. But here I'm doing it differently. I assume they follow some Gaussian distribution. So that's the crucial part. Then you may argue, this is so-called Bayesian approach. That's why this is a little bit different. You may challenge me, say, what's your rationale to make such an assumption, the Gaussian distribution? Well, yes, that is a little bit arbitrary, but Gaussian distribution, I'm not saying exactly what kind of distribution, the parameter, the mean, the variance, I don't fix them. I will let the data to find out. The only assumption is that shape. So that's, people criticize the Bayesian approach as subjective. Yes, it is subjective, but how subjective? In the traditional approach, you also make assumption about the residuals follow Gaussian distribution. I'm not doing something dramatically different from that. If you can reasonably assume the residuals follow Gaussian distribution, I can do the same thing, right? So I'm not just the distribution. I'm not saying how narrow or how spread out the distribution is. I'm just saying it's just a Gaussian distribution. So that's the only thing I'm doing a little bit different from the traditional approach. So with that, then that's the reason we call it partial pruning. We don't let those A's and the B's, the intercepts and the slopes, to go wild. They are kind of bounded, not bounded, sort of constrained by those two Gaussian distributions. That's why it's called a partial pruning or shrinkage. That's another term to describe this. So that's practically, I just apply those two assumptions, for one for the intercept and the other for the slope. So that's the only thing I do. Well, then you may ask, why is this better? Why the multiple comparison correction issue is gone? Well, that's because I only have one model. Unlike the traditional approach, if you have multiple voxels, you have as 200,000 voxels, you have 200,000 models. If you do the RI, 21 RIs, you have 21 models. I only have one model. So there is no such a thing called multiple comparison issue, right? So that issue is gone. Now also, in place of multiple testing, now I just have this so-called partial pruning. I constrain them, those 21 RIs, through this assumption, the Gaussianity assumption. So that's all. Only thing I do is need to be different, and it's not something unreasonable. That's just the distribution, right? So when I do that, I end up this is 21 RIs, 7 rows, 3 columns, 21 RIs. For this, when I apply this approach to this specific data set, so in the end, I don't have a p-value anymore, but instead I have this in Bayesian modeling, people talk about a posterior distribution. So we have prior assumption the prior assumption, basically those are I just showed you the A's and the B's there, the Gaussian distribution, that's the priors. Then in the end, I have the distributions. Distributions depend on, the vertical line is the zero value, right? So the zero. So it depends on where that your distribution relative to the zero value. This is the slope part. In this particular study, we're focused on the B, the slopes. 21 RIs, we have 21 slopes. So depending on each RI's the posterior distribution relative to the zero value, then you can talk about this evidence, whether you have strong or weak evidence, right? So that's then you still have to make a decision, of course. That decision, well, where do you want to talk about? Yeah, you can still apply the 0.05 criteria, right? Fine, you can do that, but you don't have to. You can, if it's 0.07, the tails, if it's 0.7%, you can still talk about it. We don't have to be that strict. As long as you show the posterior distribution, it's transparent. I don't want to hide anything. Unlike the current approach with whole brain, you only show the 5 clusters. The rest of the brain, you just hide it, or not just hide it. Even if you want to show, there's no way to show it. But here, when I publish a result, all the 21 RIs, I'm going to show it. So I have nothing to hide, so it's more transparent. And you can focus on some RIs. That doesn't mean as when a person reads the paper, you can also see the other RIs. This is also healthy for in the field when you do meta-analysis, for example. You don't have to, based on what the people reveal in the paper, right? That's because we have nothing to hide here. Even for those RIs, the evidence is weak. For the people who perform meta-analysis, you can still use the information, right? So that's another advantage. So that's one way to summarize the data using the posterior distribution. Of course, you can also condense them to use the error bars, of course, the standard deviation. You can do that too. Even if we use the 0.05 approach, we end up, I believe there are 6 RIs. Even if we use the same criteria, 0.05, two-tailed 0.05, unlike the whole brain analysis, we only managed to have 2 RIs to survive that approach. Or using the same criteria, 0.05, we have 6 RIs, the green bars at the right-hand side. If we loosen the criteria to 0.0 one-tailed, for example, then you can talk about the 2 extra RIs as well. So any questions about this? Yes?
If I understand this right, but if your original data you're applying for is in fact an event bias,
Blur, smoothing?
If you're blurring the original data, you're not going to impose a Gaussian on your area and expand your area. In fact, if you're looking for what are your inferences is that there's a Gaussian spread of the signal, right?
Yeah, this Gaussian is, I forgot to mention the RI is you average within the RI. It's not each voxel. So 21 RI is just that you have each subject you have 21 numbers. Of course, there you have impact about the RI. How do you define the RI? You can based on atlas, for example. That's pretty fixed. Or if people use the so-called peak voxel, you draw a bow around that voxel. Which is what the people in this study they did, based on using 6 millimeter radius to draw a bow around the peak voxel. So the smoothing part that basically you wanted the bow with a bigger radius or smaller. So that's part of the impact of smoothing. Yeah. So that's the basic approach for this. So that's second way. A third way, basically, you can further reduce summarize the data. There's 21 rows. Each row shows the mean, the standard deviation, and the quantile intervals. So there are different ways to summarize it based on the situation. So this is the mostly condensed one. So there are more information you can pull out of it. For example, one thing is that you can go back to talk about each subject, say something about each subject as well. You get the mean, get the standard deviation, get the quantitative interval. For example, you can talk about some outliers. For example, there are some more stuff which you can explore. I haven't do something about this, but that's a potential area we can in the future to see if we can do something about it. Well, then you may ask, how good your model is, right? Well, we can do something to assess the model or compare to the traditional approach. One way is to call a cross. You can calculate the information criteria, leave one out, for example. Then we compare the traditional approach. You can immediately see the information criteria, the difference between the two models. The first, that's the traditional model, general linear model. That's the information criteria. The second of all is the Bayesian approach. So immediately we say the Bayesian model does a better job. The performance is better. So that's one way to judge the performance of the model. A second way is this two plots. What are they? The first one is the traditional approach, the general linear model, right? So that's 21 RIs. You do a 21 separate general linear model. In this case, it's just simple regression. On the right-hand side is the Bayesian model. But exactly what do the curves describe? What do they tell us? Well, the black, that's the original data. Same thing. So the two black curves is the same thing. It's the same data. So that's the original data. What are the blue clouded curves? That's based on the model you want to draw, randomly generates the simulations. So, I mean, when we build a model, we can keep generating new data, right? So that's one. That's one way to that's why it's called cross validation. So to see the model performance. So using traditional model, we can randomly generate new data. So you can see the original data is the black one, the blue one is based on the model. So the difference, the discrepancy between two tells us about how accurate your model is. On the right-hand side is the Bayesian approach. Of course, the Bayesian approach is not perfect either, but I compared to the traditional approach, that's RI. I mean, it's like the whole brain analysis. Each voxel, each RI is modeled separately. So the Bayesian model does do a better job for the peak area, and also, I mean, even the tail area, it does a better job as well. So that's a second way to judge the model. There's a third way, which is a little bit esoteric. I'm not going to talk about, but that's from that criteria, the Bayesian approach also performs better. So there are multiple ways to judge the model performance. So we're not just saying, I have this, I have some prior. I mean, there's even there's a room to improve this model as well, but that's a separate issue. But at least currently, compared to the traditional approach, we do show the model is doing a better job. So that's one scenario we can adopt this approach. The second potential application is I call it cross-regional analysis. That's basically what's currently in the field. Graph theory. People use the graph theory to handle talk about so-called connectivity. I want to avoid the concept of connectivity because the word is pretty vague. I mean, people interpret that as, talk about what's it called, ages. I mean, when people say age, does that mean it's a physical existence? I talk about but anyway, let's say if we can apply the same approach to that scenario. So graph theory, I mean, there are many methods, but I'm talking about the basic one. Suppose we have this real data, 17 subjects, each subject we 17 RIs. So that means you end up each subject will have that correlation matrix, right? Suppose it's resting state data, or even task-based data, you can calculate some sort of a correlation. But anyway, we end up with a 17 by 70 correlation matrix, right? That matrix, of course, the diagonals we don't care because it's all ones. The off diagonal we can only put focus on half of it, right? Just like an inter-subject correlation. So that's end up 17 RIs end up 136 values. Focus on, for example, lower triangular part. So what do I can do with those 136 numbers, right? The Fisher Z-score. The current approach, the famous one is called, I think some people you probably know, here you probably know that is called NBS, right? Network-based statistics. That's implemented in several packages, including, I believe, CON, C-O-N, package also probably adopts that same approach. So, the idea is with 100, in this case, 136 Z-score, you just do 136 t-test, right? Now the question immediately, how do you correct for multiple testing? That's pretty much like voxels, right? In this case, instead of 100 and some number of voxels, it's 136 pairs. But how do you correct that? The NBS approach is basically they borrow the idea from the permutation test at the group level, randomized, for example, or the early version, not randomized, early version. So in that case, so they do permutations, then use the permutation as a law distribution. Then in the end, the counting number of to form some sort of clusters, they form sort of labeling. They call it ages. So the idea is pretty much similar to the permutation testing in whole brain analysis. So that's what they do. But the problem with that is they don't differentiate when they show so-called clusters, different formulation of the clusters. They don't differentiate them because those so-called ages, they have some correlations. Not all ages share exactly the same correlation. So they can't accurately quantify the correlations. So that's one trouble. But also, the bigger trouble is that they have to start with a primary threshold, pretty much like the voxel-wise p-value. When they do that thresholding, the result is can be dramatically different. Depends on what kind of a primary threshold. There's low criteria, low standard to the user what p-value, what t-statistic you want the threshold. If you read the manual, they just say whatever, anything goes. You can pick up any t-value, any p or t value to threshold. So, people have done that to show you change different p-value, different threshold, you end up with dramatic different results. So that actually is just troubling. The reason why that is, you do have that aperture is just simply because you can't accurately quantify the relationships among those pairs. That's why. It's because the model is so crude, they don't characterize the relationships. So that's basically the trouble. So we can do something better, I believe, and I'm trying right now. So far it's promising because it's pretty much like what inter-subject correlation, similar thing. We can accurately quantify to the relationships among those areas. So here is just a simple result to show you. On the left-hand side, you just do the individual t-test. On the right-hand side, using the Bayesian approach, you can say the right-hand side approach basically shows the more powerful detection. On the left-hand side, they use the network-based approach to correct for the multiple testing issue. So that's one thing. Advantage is there's no arbitrariness involved with this approach because in the end you have the posterior distribution because the model is based on exactly how you characterize the relationships. So there's no room for that arbitrariness. Also, the detection power is higher. So that's second thing. And we can do something even better for each RIs, we can say something about this. You can estimate the distribution. I forget the term in the graph theory. They talk about the hops. They talk about the hops. When they define the hops is defined how many so-called surviving connection edges. If we have more edges, that's called a hop. That's called a like concentration center in the brain. But that's just a discrete because it's based on how many surviving edges associated with each RI. Here we can do something better. I can exactly quantify the contribution from each RI. So each RI, I can say something about the contribution, the standard error, and the quantile. So we can make, based on the posterior distribution, we can make more accurate quantitative judgment about the so-called hops. So that's something, I think that the approach would do something better. Similarly, we can go back to the RI level too. Similar to the situation with different RIs. So there are more room to explore. So that's we'll keep trying. Also, we can also do the model comparison as I showed you for that theta-based correlation as well. So the model does perform better. The left-hand side is the traditional approach, the t-test approach. The right-hand side, the Bayesian-based. So that's based on the discrepancy between the original data versus the model-based simulations. So that's second application. There are two other applications, as I mentioned before. The third one would be based white matter connectivity analysis. That is real connectivity because the connectivity is based on the bundles, the white matter bundles. So in that case, you don't have a correlation matrix, but you have a matrix of white matter bundles that you can do something that would be similar to the correlation matrix, except you don't have all the elements available. Some of the elements you would say you can say there's no white matter connectivity. But from modeling perspective, it's pretty much similar because the matrix is symmetric. So that's the third application. Fourth application is the inter-subject correlation I was talking about, the naturalistic scanning. You can apply the approach to that at the RI level as well. That, I'm also doing some testing. So far, the results are also promising. So that's basically the build a Bayesian model based on the linear mixed effects model I showed you previously. So that's another potential applications. So far, I'm working on those 4 applications. So theoretically speaking, this approach can be applied to the whole brain level, at the voxel, but it's not practical for 2 reasons. The first reason is that Bayesian approach, the computation cost is just unbearable. For RI, for the previous analysis I showed you, that's about 5 to 7 minutes. That's fine. But if you do whole brain, that's I would not just I don't want to try it. That's just maybe may take years, just for one analysis. So that's the major hurdle to apply the approach to whole brain. Slightly the second problem, it's more about assumption because the voxels in the brain, the neighboring voxels are highly correlated with each other. That presents a little bit challenging, but that can be done. But that requires some work about that. But the computation cost is the major one. So that's basically this is. There are some other few limitations. The first one, we have to define those RIs, right? That can be done based on previous studies, based on meta-analysis, or can be based on atlas, right? Nowadays, there are many atlas available, so you can use that to define RI. If you don't have those sources, how can you do? One possibility is you recruit more subjects, right? Double your subjects, then use half of the subjects to define, use the second half to perform the analysis. Or if you don't double the number of subjects, you can double your scanning time, use half of data to define RIs, then use the second one to perform the analysis. So those are the alternatives. So I think that's pretty much I want to say. There are many ways you can criticize different models. Even Bayesian approach, of course, you can criticize it, but at least the approach provides a platform for us to criticize it, even if it doesn't do a perfect job. No model does a perfect job. We always start with something and go from there. So at least the Bayesian approach, we do have a platform for us to criticize, to compare to alternatives. Unlike the current approach, nobody is doing any model comparison. Nobody is checking their model performance. We just have a assembly line. We use the software, just go through steps. Then we have the results. If we are happy, we just already publish the results. Nobody question the model whether it's valid or not, right? Nobody doing anything about the model, challenging the model, right? So that's here we can directly show the model performance, check the model's performance from different ways. So I think that's pretty much I wanted to see. This is just a summary of this start precision.